You ever stop and think about what's actually running things deep inside your computer? Under the hood of your operating system, your browser, even the games you play? Well, you might be surprised to learn that a lot of it comes down to a programming language from all the way back in the 1970s. Turns out it's the invisible bedrock of our entire digital world. Today, we're diving into C. So here's our game plan for today. We're going to kick things off with why C is such a foundational piece of the puzzle. Then we'll follow the trail of how a simple line of code actually becomes a command the computer understands. From there, we'll dissect a C program to see what it's made of, get into its basic building blocks, and then wrap it all up by looking at why this nearly 50-year-old language is still so incredibly important.
All right, let's jump right in with our first section, C, the world's foundation. We're going to explore how a language born in the 70s is still, somehow, running just about everything.
This timeline really puts it all in perspective. It all kicks off in 1972. A guy named Dennis Ritchie at Bell Labs needs a better way to build the Unix operating system, so he creates C. Just 6 years later, the now legendary K&R book comes out, and the language just explodes in popularity. And by 1983, C was so important, so fundamental, that ANSI, the American National Standards Institute, had to step in and create an official standard for it. That's when you know something's a big deal. So, what's the secret sauce? Why did C take over the world? Well, it boils down to these key things. For one, it's a general-purpose language, which means you can build almost anything with it. It's also super portable, so you can write code once and run it on different computers without a ton of hassle. And, of course, it is famously incredibly fast and efficient. This combo made it the absolute perfect choice for what we call system programming, building the actual operating systems and compilers that everything else relies on.
Okay, on to our next section, from code to command. So how does an idea, something we type into a simple text file, actually make a computer do something? Let's trace that fascinating journey. It all happens in these 4 main steps. First, you, the programmer, write the code. That's the source code. Then, a special program called a compiler takes your human-readable code and translates it into machine language. But hold on, it's not quite ready. Next, the linker jumps in and pulls together all the different pieces, connecting your code to pre-written library functions. And finally, the loader takes that finished package, puts it into memory, and tells the computer, go. It really is like writing a recipe. You write the steps, a translator prepares it for a robot chef, the chef gathers all its tools, and then it starts cooking. In this diagram here, it maps out that whole process perfectly. You see, we start with the programmer creating that source file. That file then gets fed into the compiler, which spits out machine-readable object code. But it's not a complete program yet. That's where the linker comes in. It grabs any functions it needs from libraries and stitches everything together into one single final executable file. And that's the thing your computer can actually run. All right, so we've seen the how. Now let's dig into the what. Let's get our hands dirty and look at the actual blueprint of a C program. What's it really made of? Pretty much every well-written C program follows this basic structure. It's a logical flow. You start with documentation, comments for other humans, then comes linking, definitions, and any global declarations. But the real heart of it all is the main function, which is then followed by any other subprograms you've written. This structure just keeps everything organized and makes sense of the code. Now, that linking section is super important. You know that hashtag include line you see at the top of pretty much every C file? Well, that's what this is. It's you telling the compiler, hey, heads up, I'm going to need the standard library of tools for things like input and output, so go grab it. It means you don't have to reinvent the wheel every single time you want to do something simple like printing text on the screen. And now we get to the absolute, undisputed heart of every C program, the main function. Every single C program has to have one of these. It's the official starting line. When you hit run, the computer immediately looks for main function and starts carrying out your instructions from there. Seriously, no main, no program. It's that simple. Okay, let's grab a magnifying glass and zoom in even closer. If a program is like a set of instructions, what are the actual words and punctuation we use to write it? Let's check out the language's fundamental building blocks. In C, we call these little pieces tokens. A token is the smallest possible thing the compiler can understand, whether that's a command word, a name you made up, a number, or a symbol. Absolutely everything in a C program gets broken down into these tokens, and having this direct, fine-grained control is a huge part of what gives C its legendary speed. This chart breaks it down beautifully. Every single token in C falls into one of these 6 buckets. You've got your keywords, which are the language's built-in commands. Then you have identifiers, those are the names we create ourselves. You've got constants and strings for your data. And finally, special symbols and operators that do all the work, like adding numbers or structuring the code. So let's start with keywords. You can think of these as the official, reserved words of the C language. They have a very specific meaning to the compiler, and you absolutely cannot use them for anything else. And here's the wild part. The entire powerful C language is built on just 32 of these keywords. That's it. And there they are, all 32 of them. It's kind of mind-blowing when you think about it. Every command for making decisions, for looping, for defining data, it all comes from this tiny, powerful vocabulary. This lean approach is a huge reason why C is so darn efficient. There's just no fat to trim. Words like if, for, while, return, that's the core of it. Okay, so if keywords are the words the language gives us, identifiers are the names that we, the programmers, get to create. Anytime you need to store some information, like a user's age or a score, you give that little slot in memory a name. That name, age, or user score, is an identifier. Of course, you can't just name them anything you want. There are a few rules to the game. An identifier can only have letters, numbers, and the underscore. It has to start with either a letter or an underscore, and obviously you can't use one of those 32 keywords. And a really important one, C is case sensitive. So name with a capital N and name with a lowercase n are 2 totally different things to the computer. So, after all these nuts and bolts, we have to ask the big question. Why are we still talking about a language from 1972? Let's tie all this together and see why C is still a titan in today's world, powering everything from your smartwatch to giant internet servers. This quote just nails it. C wasn't just another language to come along. It was a fundamental shift in how we thought about telling computers what to do. It gave us a structured, powerful, and efficient way to translate our logic into machine instructions, and that idea has influenced everything that's come since. And you can see that influence everywhere. Languages like C++, C#, Java, even Python, they all have C's DNA in them, borrowing its syntax and its core ideas. But don't think for a second it's just a history lesson. C is still the champion when you absolutely positively need performance. We're talking operating systems, tiny embedded systems in your smart devices, high-performance game engines. When speed is king, C still wears the crown. Honestly, learning C is like learning the Latin of programming languages. It helps you understand where so many other languages come from. And all this leaves us with a pretty big thought to chew on. Q created a revolutionary new way for us to have a complex conversation with machines. As we barrel into this new era of AI and quantum computing, you have to wonder, what's that next great conversation between humans and machines going to look like?